this is where we are. We're in week 1 of simple harmonic motion. As it loads up, let's go into what our warm-up is. So nobody cheat on the warm-ups, right? Let's totally be honest with this and let's look at it and not go ahead. Because if you go ahead, then you're just gonna be yelling out answers that you already know the questions, all that sort of thing. So a mass is oscillating up and down. That means it's moving up and down on the spring, okay? 3 students are discussing the acceleration of the mass. Eileen says, I think the acceleration of the mass will be largest when it is at the end of the oscillation turning around. That's when the spring is stretched the most. Bridget says, no, I don't see how that can be. Its velocity is 0 at that point, so its acceleration has to also be 0. There's my last student. And then Chandra, we'll go with Chandra. I disagree. The acceleration is largest when the mass is halfway between the middle and the end because that is where the speed is changing the most. Okay, so let's just think about this for a minute. You've got a spring and you put a weight on it, and you pull it down and let go, and you just watch it go up and down because, I mean, you're bored. What else are you going to do during winter break? It's moving up or down. And when it's oscillating, we're going to talk about where the acceleration is the most. What do we think about the acceleration on this mass? I'm going to go ahead and stop the share because there's no reason to stare at this any further. What do we think about the oscillation on this spring? Or where is the acceleration the greatest? What's this? Where's the spring? Where's that weight trying to get? You guys got to talk to me.
To the center?
Yeah, it's trying to get to the center. So if it's trying to get to the center, when it's at the center, do you think that it has a large acceleration or a small acceleration?
Small acceleration.
Say it again.
Small acceleration.
So if it's at the middle, if it's trying to get to the middle and it's at the middle, that means it would have a small acceleration or 0 really, because it is where it wants to be. So that means when it's completely stretched, the spring, or up where it's completely compressed, it's the furthest away from where it wants to be. So then it should have the largest acceleration, right? The further away you go from where you want to be, the more force there is, therefore the more acceleration there is to return to that middle portion. So that's what we're going to talk about over the next week is simple harmonic motion. And it's a lot about trying to get to the center, get to that equilibrium point. So let's take this conceptual thing we all kind of understand. We know that if you have a pendulum on like a grandfather clock, you guys ever see a grandfather clock, or is that really too old for your generation? All right, so nod or don't, or like move. I think everybody took a picture of themselves and they put it up to the camera. That or everybody's frozen, but I see a ceiling fan moving. I see, I got a thumbs up, perfect. So we've heard of a grandfather clock, you know, it's got the whole pendulum at the bottom, tick, tick, tick. And if we were to stop that pendulum at any place and it stays stopped, that would be at the center, at the bottom. If we stopped it up at the top right or the top left and let go of it, it would continue to swing because it's trying to get to that equilibrium, that middle point. So the further we pull away from it, the more acceleration, the more force it's going to have trying to bring it back down to that point. Let's look at it graphically. I think sometimes that helps warm us up into what we're talking about. And let's get some definitions as well. So let me go back to this other computer. Application, Chrome. And let's go to this grid. All right, so I'm going to give you some definitions. And we can look at it graphically as well. Don't worry, I'll talk slow because, I mean, come on, it's the first day back from break. I had to be here yesterday, but it didn't feel like a normal day. So let's do this. Let's define first periodic motion. All right, periodic motion is motion that repeats itself in a regular time interval. So periodic motion repeats, and let's say regular time interval. So couldn't we say the Earth has periodic motion? Doesn't it repeat itself going around the sun in a regular time interval? I mean, we can even time how long it takes, we call it a year. A wristwatch, I mean, mine's digital, but a watch has periodic motion. It repeats itself. If you have a second hand, that second hand goes all the way around and it repeats itself every minute. The minute hand goes all the way around and it repeats itself every hour. And then the hour hand goes all the way around, repeating itself every 12 hours, right? Because that's how long it takes to do one period, one time around. So periodic motion is just anything that repeats and it has a regular time interval. Okay. Now, simple harmonic motion, I'm going to just abbreviate SHM, simple harmonic motion, is periodic. Okay. But it's a special type of periodic motion. It's a periodic motion with a restoring force. Restoring force. What is a restoring force? Well, I'm glad you asked. So restoring force. And this is a force that tends to bring an object back to equilibrium. Brings objects back to, I'm going to use EQ for equilibrium, just for shorthand. So periodic motion, you've got a motion that repeats itself at regular time intervals. And then there's a special type of periodic motion, which is simple harmonic motion. It is periodic motion, but it has a restoring force. It is a periodic motion with a restoring force that tends to bring an object back to equilibrium. So if we were to define simple harmonic motion, we would say that simple harmonic motion is periodic motion in which the restoring force is proportional to the displacement. Don't worry, I'll write that one out. So let's see what I need to write. Periodic motion in which the restoring force, ooh, did too many letters there. Simple harmonic motion, periodic motion in which the restoring force is proportional to the displacement, meaning the further away you go from equilibrium, the greater that restoring force is. And we can remember this back from Hooke's law. Remember Hooke's law, the force of the spring was equal to the spring constant times the displacement. Well, that means that that force is going to get bigger as the displacement gets bigger. That's what we're looking at here. The further away we are from equilibrium, the larger the force. So if we're at equilibrium, the restoring force would be zero because you are where you want to be. You're chill. You're just hanging out, right? So if you make it back to the equilibrium at that point, you're like, cool, this is where I want to be. All right. So some other terms that we're going to need to be aware of are period, frequency, and amplitude. But before we get into those, let's look at this graphically because I think it helps explain. I'm going to scroll this up just a bit, but don't worry. If you didn't get these written down, there'll be a recording. You can go back to the recording, right? Or you can take a quick screenshot. Let me check the chat because it looks like something popped up. What is the U in? Oh, no, that's not a U. That's SHM. I'm sorry. My penmanship is acting like it's a Monday morning. Simple harmonic motion. Sort. That's Tuesday, though. That means you're coming here on Friday. I don't know. Yeah. All right, so simple harmonic motion. That's SHM. It's just poor writing. Okay, let me move the chat over so I can monitor it a little bit better. All right, let's look at a graph. We can look at this graphically. Let's see if I draw a pretty graph. Do a shape, make it purple. That way. Do it that way. All right, and then let's see if we start the graph here. And then I'm going to try to draw a pretty graph, but we'll see how it turns out. All right, imagine that graph being symmetrical, just for grins, okay? pretend with me that it's symmetrical. We're going to say from equilibrium to the crest at the top of a wave, this is an amplitude. That's the amplitude. From the equilibrium to the crest is an amplitude. So then from the equilibrium down to the trough, that is also an amplitude from there to there and from there to there. So from crest to trough, from very tip top to very bottom, that would be 2 amplitudes, right? Because from your equilibrium, the horizontal axis being equilibrium, going up to the highest point is 1 amplitude, and from the equilibrium point to the lowest point is also 1 amplitude. If this is a displacement graph, then we know that the slope is velocity, right? And what would the velocity right here be? Velocity right here would be equal to what? At this point right there.
0.
0, absolutely. All right, then what about velocity down here?
0.
0. That's the point at which it's changing directions, right? It was going down, now it's going to start going up. And at the top, it was. So we can do this for each of these points. We can say velocity equals 0. Down here, velocity equals 0. And for grins, we can say up here, velocity equals 0. Awesome. At equilibrium, what is the acceleration? Now we've talked, so before anybody answers, so since there was kind of a pause, we said that at equilibrium, that's where we want to be. So the restoring force would be 0. And if the force is 0, acceleration would also be 0. We also know that since the slope is velocity, coming through here, this would be a constant velocity at this point, meaning that the acceleration is 0. So kind of 2 ways to look at this. So at equilibrium, acceleration is 0. And I'm going to use a lowercase a here so that we don't confuse amplitude, the uppercase A, acceleration, lowercase a. So anywhere that we cross the axis, acceleration is 0. Acceleration is 0. Acceleration is 0. Okay. At the top, which direction is acceleration pointing? Up or down? Down, perfect. I saw hand motion, so don't pretend like you can. All right, so we have acceleration is pointed downward here. That means over at the bottom, acceleration is pointed to the up. Up here, acceleration is pointed down. Acceleration is pointing up. So acceleration is always pointing towards equilibrium. Make sense so far? And here, velocity, if I kind of draw an arrow, if we said, okay, well, velocity here, that's velocity is going down. Here, velocity is going up. Velocity is going down. And then velocity is going this way. Try to clean this up just a little bit. So the slopes indicate our velocity. We can see that acceleration is always pointing towards equilibrium. And velocity is 0 at the tops and the bottoms. Where is acceleration the greatest? Where do we have maximum speed? Regardless of direction, where do we have maximum speed on the graph?
At the tops and bottoms.
Well, I have
Speed,
velocity being 0 at
at
the
the
tops and
middle.
bottoms.
That's the middle.
At the middle, right? Because what happens is you've got an acceleration pulling you towards the middle. So your velocity is increasing and increasing and increasing, or I'm sorry, your speed is getting bigger. The magnitude of your velocity is increasing as you're approaching the equilibrium. That means you're getting faster and faster and faster. And when you hit equilibrium, the acceleration stops and you go sailing right past, you overshoot equilibrium. And then at that point, acceleration turns around and points in the opposite direction, which would then slow you down. And then you hit that furthest point on the other side, and acceleration has slowed you down to a 0 velocity, turning your velocity around facing the other direction. And then it starts speeding you up back towards that equilibrium point. And you start at 0 and you start going faster and faster and faster and faster, and you overshoot where you want to go. So then acceleration changes direction and it slows you down to 0, causes you to change direction, turn around, and start heading back towards equilibrium. It's this constant overshoot of where you want to be. Your highest velocity is at equilibrium. At equilibrium, your acceleration is 0 because that's where you want to be. But the problem is you're moving so fast, you overshoot it and keep going. Does that make sense? When you look at it this way, is it coming together a little bit? Don't worry if it's not. You can always take the class again next year. That's a joke. Come on, smile. I swear half your cameras look. Somebody said no in the chat. All right, we've got this graph. Make sure you take a screenshot of this if you didn't write it down. All right, make sure you have this. We're gonna take this and we're gonna apply it to a spring and a pendulum. Almost everything, I wanna say everything we could do is about a spring and a pendulum for simple harmonic motion, but if I say it's gonna be that way, someone's gonna find an exception. So let's say mostly it's all about spring and pendulum. I wanna apply this to a spring and pendulum in a pictorial form. We'll go back to a couple definitions, give you 3 formulas, we'll practice them, and then we'll call it a day. All right, so you've had time to screenshot that while I was just babbling along, so I'm gonna scroll this up. All right, let's take a picture. So let's do, let's say a spring. All right, if I have a spring, this is my spring. I know it's gorgeous. I majored in art, not. All right, there's my spring. And let's just say that's its chill spot. So we'll call this equilibrium. Let me do a dotted line far enough across so I've got plenty of place. So this is my equilibrium. Again, I'm gonna use EQ for equilibrium. That's not an official abbreviation. That's just, Watley is not gonna write out a word that he'll probably misspell abbreviation. So if we're cool with EQ being equilibrium, awesome. So now if I were to take this weight that's just chill, it's happy, it's just hanging there, not moving. And I'm like, you know what? I always like to touch things. I was always the one that would go to the museum that said, don't touch the art. And I'd reach over and touch it. I'm sorry. That's just like, you tell me not to do something. It's like what you want to do. So let's say I take that weight and I pull it down and then I let go. At that point, we know it's going to try to get back to equilibrium. It's going to overshoot. So what is that going to look like? All right. So then I'm going to take this spring and I pull it and I kind of stretch it out. So it doesn't have the little waves in it anymore. And let's just say I pull it down to there. And then this would make this from here to here, that is the amplitude, right? Because that's how far away it is from equilibrium. And then when I let go of it, it's gonna shoot back up and that spring is gonna compress nice and tight. And then let's say it goes up to here. So from here to here, oh, I kind of overdrew that one. Let's say from here to there, that's also amplitude. Now, this is not drawn to scale, so no one say, well, you pulled it down 3.5 squares or 4 squares, but it only went up 2 squares. All right, just bear with me. All right, I'm not drawing it to scale. Just know that it's an amplitude. As far down as it goes below the equilibrium, that's how far above the equilibrium it goes. Both of those are marked as a amplitude. So those amplitudes are equal. Up here, when you're at the very top, we know that acceleration is maximum and it's pointed downwards because that's where the equilibrium is, right? And then on this first one, when I pulled it down here, acceleration is maximum and it's pointed upwards. Careful now, bless you. So we know we've pulled it down, amplitude, the acceleration is maximum and it's pointed up. As that spring pulls it up and overshoots equilibrium, goes to a full amplitude up, acceleration reaches its maximum and it's pointed downward because acceleration is always pointed towards and everybody thinks equilibrium in their head. So in reality, all the amplitudes are supposed to be equal. Yes, all the amplitudes are equal. It's just my inability to draw to scale. So you, though, get your ruler out, whatever. Sure, yes, the amplitudes are equal to each other. A is equal to A. Our capital A is equal to capital A. How about that? Now, the displacement of our object at the end of the spring, then, the change in the X position is equal to two amplitudes, right? From its very bottom position to its very top position, it moved two amplitudes. Cool. All right, awesome. That gives you a visual representation of a spring. Let's take a look at a pendulum. All right, I'm gonna scroll this up. I'll give you a second if you need to hit screenshot just to see my beautiful work and to post it online and say how ugly it is. That's okay, I can handle it. There you go, that was your opportunity. There we go. All right, so what about a pendulum? Let's see, I'm gonna draw, there's my pendulum right there. There's my weight, my object for the pendulum. And then if I were to pull this pendulum back to the, let's say the left side, it would show up. I'm just gonna do it dotted so we know that it's like, hey, what if it was over here? And then it swung through and then it ended up, let's say it would be over here, right? Because it's gonna tick back and forth. We know that at the highest point on the left side, this is our max acceleration, and it would be pointed that direction. And over here, this is our max acceleration, and it's going that way. And it's not maxa, that is max acceleration. So let me put a little, what if I put it there? Max acceleration are on your highest points on either side, and the acceleration is pointed back towards the center. Here's your equilibrium. Actually, I'll try to spell it. Equal, is it two L's? I'm gonna say two. Okay, equilibrium. At equilibrium, we know that this is our max velocity because as we approach it, the acceleration is in the same direction as we're going. So our speed is increasing. The magnitude of our velocity is increasing. And just as we pass equilibrium, that's when the acceleration changes direction and starts slowing us down. So we have our maximum velocity there. And at equilibrium, we remember that our acceleration is equal to 0. Okay, so what do we have? Would the amplitude be curved? No, you could determine the amplitude by the height. Let's call the height here. If we call this 0, we would just say, what is the height here? And you would look at the difference in height for the amplitude. How far off the ground is it? Let's say that the pendulum at equilibrium, it's at ground height or a height of 0, origin, whatever you want to call it. And then you lift it up, you would say that how high it is, how high it's lifted. Yes, I know it's following a curved path, but it's still dependent on how far off of the origin, how far displaced in the vertical is it. We don't care about the curved part of it. Not really. All right, let's go back to terminology and formulas, and that will bring us into our practice work. Okay, so I'm going to scroll this. Oh, I can't scroll that up any further. We need more room. All right, here, I've got to clear some spots because I have completely overwhelmed my page. Let's delete this. There we go. Now we got room. All right, so we left off with defining simple harmonic motion. So let's just make sure we've got some other terminology here. The period. Do we remember what a period is? That was in our formulas for circular motion. We talked about a period. Period is the amount of time it takes to complete one cycle. So this is measured in seconds. So seconds per cycle, seconds per revolution, wasn't that? Seconds per revolution. I'm going to put IE. Put the wrong word here. How long does it take to go around once. All right, seconds per revolution. Whatever your starting point is, getting back to that, doing a full cycle, how long does it take to do a full cycle? Or how long does it take to go around one time completely? So if you're at a pendulum, it's not going from let's say we're going to start at equilibrium, and then it goes to the right, and then it comes back to equilibrium. That's only half of one period, because one period is one full cycle. So if you're at the equilibrium and it goes to the right, it passes through equilibrium, goes to the left, and then it comes back to equilibrium. That would be one full cycle. It's done its full rotation and it's ready to repeat. That is a period. And it's the seconds it takes to do one time around, okay? A period is seconds per revolution, or seconds for one cycle, however you want to think about it. Now I'm going to add another word that we may have used a little bit to solve some problems, but we didn't focus on it, and that's going to be frequency. Okay, now frequency is the inverse of period. This is the number of cycles in 1 second. So period is how many seconds for one cycle. Frequency is how many cycles in 1 second. Okay, if you're able to determine what the period is, frequency is equal to period to the -1 power, because it's the inverse. You take one and you flip it, you get the other. All right. If you're like, well, how do I flip things? Look on your calculator. If you've got I have a TI-84. That's the most popular one. And then that I see around here. If you look where your number 7 is on the keyboard, on your calculator, and then to the left of the 7 is a log button. Above that is x squared, and above that is x to the -1. That x to the -1, that's your flipping number, or your key. That's going to give you the inverse. Okay. If you've got the period, if you use the period to the -1, that gives you the frequency. If you've got frequency, do frequency to the -1, and you've got period. They are inverses of each other. One is cycles per second, the other is seconds per cycle. You see how even the units are flip of each other. Seconds over cycle, cycle over seconds. I don't know, it's not that bad. All right, and then we've talked about amplitude being the displacement of the object at its extreme from equilibrium. That's no big deal. Let me give you formulas. There's 2 in the notes that show up on Canvas, and there's 1 that doesn't. So I need to make sure you have all of those. So let's get down to business and do the formulas. So I'm just gonna draw a line. All right, the period of a pendulum. So let me write that. Period of a pendulum. T is our designation for period, capital T. All right, capital T is period. And then the P, that subscript P, that means for a pendulum. So that's period for a pendulum. And this is equal to 2 times pi times the square root of L over G. Now, L is equal to the length of the string, and G is equal to acceleration of gravity. All right, length is going to be in meters. Don't forget that. So the period of a pendulum is 2 pi times the square root of length divided by gravity. For pi, use 3.14. Use 3.14. In a lot of our practice work, if you want your answers to align with the answers in the, where it says it gives you the answer and you're trying to determine it and see if you get the right thing, most of the practice problems use 9.8 for gravity. You can use 10 and just know that your answer is going to be a little bit different than theirs. And as long as you're close, you know you got the right thing. If you really want to make sure that you're getting the exact same thing that the solutions listed, 9.8 will do that. Okay, your choice. It's just what you want to type into your calculator. All right, now we need to do the period for a spring. So I need to clear some more space. All right, period of a spring. The T still is period. That little subscript that looks like a squiggly, that's my S. So period of a spring, this is equal to 2 pi. So far similar, easy, times the square root of the mass that's on the spring divided by the spring constant. Okay, so M equals the mass on end of spring, and K equals spring constant. All right, I've got one more formula to give you. It's not listed
Mr.
there.
Watley,
Yes.
would the mass still be kilograms?
Yes, mass is in kilograms.
Mr. Watley,
Yeah, what's up?
for the acceleration of gravity, is that just the 10? Is that just the 10 value like that we've been using?
Yeah, unless it tells you something like, hey, you're an astronaut, or something weird's going on, it would be the 10 that we're using. Now, for some people really want their answers to be the exact same as what's listed in the problem, and I just warned that the problems use 9.8. So
Okay.
if you want your answers to align exactly to what's in the worksheets, use 9.8. If you really don't care and you're just making sure that yours are really close, 10 is going to work. Either one is completely legitimate. So just depends on if you want to type 9.8 into your calculator, if you want to type 10 into your calculator. Either
Okay.
one is fine. But yeah. All right, the very last one the formula that I have, this one only comes up a lot in our practice problems. It doesn't come up, I don't think, really in the AP exam, but it is on your formula chart and it is in our practice problems. So let me give you this, and this is going to be X is equal to A, capital A, so we know that's amplitude, times the cosine of 2 pi times the frequency times the time. Now, for this, your calculator has to be in radian mode. You have to be in radian mode. This is so rare that we use radian in physics, but because you're taking the cosine of 2 pi, you have to be in radians. Now, for this formula, X is your displacement. Capital A is your amplitude. Pi, remember, use 3.14. This F is your frequency. And T is your time. So if you get a problem, you've got 3 different formulas that we're going to be focusing on. Depending on your given, you're going to select your equation. You're not abandoning your guess method that we used from the first week of school, where we look at the problem, read it, we identify the given, we look and see what the question's asking us for, we pick the equation, we rearrange the equation, and we solve it, okay? These are your 3 equations that we're going to use through simple harmonic motion. I don't think there's anything else that comes up. Let me make sure everybody's got those. If there's any questions about those, let me know. And we've got a bit of time. I'm going to do on the notes that are in Canvas, we're going to breeze through the backside of it on the problems there. I will get you started on the practice problems for simple harmonic motion and then let you finish it up for next class. realistically, if we're able to kind of clip through this, you should only have like 4 problems to do after we're done. Maybe a little bit more depending on the speed that we move. All right, so we've got our 3 formulas. If you don't have them down, take a screenshot. It is in the notes. You can get to them all except for that last equation I just gave you. It does not show up in the notes anywhere, so make sure you have that one written down somewhere. All right, so if we go to this page, it comes from Canvas. You'll see that, wow, those are I gave you these definitions almost word for word. I just gave you these 2 equations, and I gave you a third one. I complemented those things with the graphs that we did or the graph that we did and the pictures. So now we're just going to go over to this and kind of answer through this part of it. So I'll rotate this back around. Okay, so what do they give us? They give us a displacement graph for an oscillating mass on a spring, which is perfect because we've already seen a graph just like this, right? You've got it in your notes. We've got something we can refer back to. So the first question says, what is the period of this oscillating spring? So someone take a look at the graph and yell out or put in the chat, either way, what is the period for this spring? No formula required. How long does it take to get through one cycle? Yes, yes. 2 people so far in the chat, 3. Let me get at least a couple more. All right, I got 4. Let me get 1 more. Whoa. All right, back that one up. Most of them were right. We started at the amplitude being 4 meters, right? And the spring goes down through equilibrium to a -4, comes back up through equilibrium, back up to a +4. So how long did it take to go from +4 back down, back up to a +4? 8 seconds is our target. All right, 8 seconds is our period. That's how long it took to do one full cycle. So I'm going to fill this in. 8 seconds. What is the frequency? Okay, well, what did I tell you about frequency? How do we calculate frequency if we know period? It's the inverse, right? So if we were to take the inverse, if we put in our calculator, we would get 0.125, which is also just 1/8. And then frequency is measured in hertz. That should be an HZ.
Mr. Watley,
Yes.
would you mind repeating what we have to use to find the inverse on the calculator?
Yes. Can you see my screen, like me?
Yeah.
All right. So if I show, all right, on my calculator, it's that button right there. See that X to the -1?
All right. I have it. All right. I got it. Thank you.
No problem at all. Why would the period be 8 and not 16? Wouldn't 16 period because this is one full cycle? Okay. So I'm being asked about let me make sure I'm answering the right thing. Why would the period be 8 and not be 16? Wouldn't 16 be the period because it is one full cycle? What we're going to see is we are starting right here, right? We're starting at the 4 meter mark and we're going down. So what I'm going to ask you is, in your head for everybody, when do we return to the 4 meter mark with a direction of going down? Because that's where we're starting. We're starting at 4 meters and we're going down. When do we get back to that place? Well, right here, we're back to 4 meters and we're going down again. And then it would come back up to here, right? That would be another cycle. So if the graph went as far as I just drew, it's graphed 2 full cycles for us. We started at 4 meters and we're going down. Okay, so we went down, back up. Well, that's one full cycle because we're back at 4 meters and we're ready to go down again, down and back up. All right, perfect. And then for frequency, so I see something on here that says, okay, do you prefer decimal rather than a fraction? Oh, most of the time, 90% of the time, I prefer a decimal because 1/8 is the same as 2/16. You know, you can give me an infinite number of fractions that equal only 1 decimal. So most of the time, I like the decimal. In this case, the fraction is cleaner. And so either one is legitimate. I will accept either. But if you give me a fraction that could be simplified, I'm not going to accept it. So if you gave me 2/16 and say, well, it's right, I'm like, yeah, no, sorry. So in this case, 1/8 looks to me cleaner than 0.125 hertz, but either one is legitimate. Either one's legitimate. So just make sure if you do a fraction, it is a reduced and clean fraction. If it looks like a crazy number, and if I look at it and it looks like craziness and I've got to put in a calculator to figure out what it's supposed to be, just don't do that. Okay, let's see. What is the amplitude? All right, so in the chat or out loud, tell me what the amplitude is. 4, absolutely right. So that's how far we are from equilibrium, 4. And that'd be 4 meters. What is the position function for this oscillating mass? Do you remember what kind of graph this is? All right, from your math class, do you remember what kind of graph this is? Sine or cosine?
Cosine?
Cosine, yeah. It's a cosine graph. So we would say that x equals cosine of theta. I'm going to go back because I did see in the chat that someone wanted me to just kind of hit on one time again. In order to determine the period, we're going to find one place on the graph. And here we started at displacement at 0. And at that point, we were at the 4 meter mark and we were headed down. And I said, okay, how long does it take for you to get back to the 4 meter mark and be ready to go down? And that was at the 8-second mark. So at 0 seconds, we were at 4 meters going down. And then we came back at 8 seconds, we were at 4 meters ready to go down. And then at 16 seconds, we would again be at 4 meters ready to go down. So you look and say, okay, you can pick any part on the graph. We could have picked right here at the 2-second mark, and we say, hey, we're at equilibrium with a negative slope. Well, at 6 seconds, we're also at equilibrium, but that's a positive slope, so that's not the same thing. But then we get to the 10-second mark, and we're again at equilibrium with a negative slope. So from 2 seconds to 10 seconds, that is an 8-second time lapse. And so that gives us the ability to see that it is 4 cosine theta, Mr. Oh, the number doesn't matter for this one where it says, what's the position function? It's only asking for the function. So we only have to say cosine. We're not solving for it. It's just asking for the function. So we would say that this is the cosine of theta because it's a cosine graph. It's not getting, too technical. All right, let's.
Mr. Watley?
Yeah, what's up, Pies?
I'm just a little confused on the amplitude part. So are there going to be graphs or oscillating masses where they start at displacement 0?
Displacement 0 will always be identified as your equilibrium point. Any movement from 0 will be movement away from equilibrium.
Right. So let's say we had like a graph just like this, and instead of starting at like 0, 4, it started at 0, 0. Like, would that happen? Can that happen?
Yes, we could have started this graph at the 2-second time point, and it would show that the object was in motion when we started. I guess the reason it shows it at the 4 meter mark is because it's kind of like, hey, what if I pulled, let's say this is a spring, actually it says oscillating spring. We pulled the object 4 meters and then we let go and that put it in motion. If you start an object at equilibrium, most of the time it's just going to sit there because it has no reason to move. And so it makes most sense to have the graph start at the highest amplitude because it's showing, hey, it is displaced and now it is trying to return to equilibrium, and we can see how it overshoots it due to that velocity it has at equilibrium.
All right, I got it. Thank you.
No problem. All right, let's look at what it's telling us to do on the position displacement versus time graph. mark in red all the locations in which the velocity is 0. Okay, so if we want to mark this drawing, come on. We need what, red? All right, so if we have, did that give me red? Nope. All right, so I'm not going to worry about the colors. Let's see if I do purple. Oh, there's red. Okay, so where the velocity is 0, we know the velocity is 0 here, 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 there, and there, right? The velocity is 0 at the troughs and the crests. In blue, all the locations in which the magnitude of velocity is the greatest. Okay, in blue, well, I've got this color. I'm going to use that color. Well, the location where the velocity is the greatest at equilibrium. Okay. All right, so we've followed all the directions. We've kind of done that portion. I'm going to scroll this up just a little bit. Actually, if I shrink this in, I can see the next graph. I think that still allows us to kind of see what's going on. Using the data points you've indicated on the position versus time graph to plot a velocity versus time graph on the right. Okay, so we need to plot a new graph, and this one's going to be velocity. Well, if we know the starting point at the beginning, the velocity was 0. So that means this one has to start at velocity 0, right? Because the position graph starts at velocity 0. This one's going to start at velocity 0. And then we have a negative velocity, so that means it's going to go down to here. And then it comes back up, and this was a 0 velocity. See, it has these vertical lines to help us kind of correspond. When it hits the, on the next one, when it hit the axis, that's our highest velocity. So it'd be like up here, then it went to 0. Then we had a negative velocity, and then it went to 0, and then we had a positive velocity. So if I drew this, man, it's gonna be a horrible drawing. It should look something like this. And this should be kind of curved. It shouldn't be sharp. Something like that. There's my velocity graph. When velocity was 0 at 6 seconds, I'm sorry, not 6 seconds. The velocity was 0 at 0. Velocity was 0 at 4. I'm looking at the first graph. I see velocity was 0 at 8. So it's going to correspond with my velocity graph. It says on the velocity versus time graph to the right, mark in orange. Okay, I think I have orange here. That's orange. All the locations at which the acceleration is 0. Let's see, the acceleration is 0. The acceleration is 0 here. The acceleration is 0 at 6 seconds, at 10 seconds, and at 14 seconds.
Mr. Watley,
Yes.
I thought the acceleration was 0 at the equilibrium.
Look at the display, look at our first graph.
Oh,
Yeah, refer back to that first graph. If you look at that first graph, we knew that it's the displacement. That's a displacement graph where we can see equilibrium. In the velocity graph, we can't see equilibrium anymore because this is a velocity graph and not a displacement graph. So we don't have a location on the velocity graph. The next one says in green, all the locations, so marked in green at which the magnitude of the acceleration is the greatest. So when is acceleration the greatest? Acceleration was the greatest at, so when velocity is max, acceleration is 0. Correct. Velocity, when velocity is max, acceleration is 0. That's absolutely right, because velocity was max at the equilibrium. So if we go to our maximum velocities, those are ones that are going to be the acceleration 0. Let me go green. Let me make sure I read this through in green. All locations in which the magnitude of acceleration is the greatest. So we have the greatest acceleration. Well, hold on a second. Let me think this through. So when velocity is max, acceleration, yes, correct. But this is asking for the acceleration is the greatest. So greatest acceleration would happen here, 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 here. And again, for me to do this, I'm not that deep of a thinker, I guess. I'm still looking at the displacement graph because I can visualize that one and understand it the best. So then I just kind of refer back to the time points there to get a good understanding of how to draw it. All right, the next one says, use the data points you indicated on the velocity versus time graph to plot an acceleration versus time graph at the right. And then it wants us to mark some stuff. So in this case, let me go back to my black marker. Here, it should be something like starts negative, goes to 0. If I come back up, back and forth, let's see. And then this one goes positive, and then 0, and then negative, and then 0, and then positive, and then 0. Because if we come back up, which way was acceleration pointed in the beginning? It was pointed down, so that's negative. We come down and we mark it negative. At that next vertical, at the 2-second mark, we're at equilibrium, so acceleration should be 0 because we're at the equilibrium, so we marked it 0. And then you kind of just follow the pattern from there. It should be something like this. All right, and it asks us, at the locations where the magnitude of the acceleration is the greatest, what can you say about the net force? Well, if the acceleration is the greatest, that means the net force must be also at its greatest. The velocity, what's the velocity? When the acceleration is it's the greatest, what's the velocity?
0.
0, absolutely, good job. And then what about position? Do we have our maximum position? Are we at equilibrium? What's our position?
Amplitude.
The amplitude.
Yep, we're at the amplitude. Or we can say maximum displacement, whichever you prefer. Okay. At locations where the acceleration is 0, what can you say about the net force?
It's balanced.
If the acceleration is 0, what does the net force have to be?
0.
0. Okay, what about the velocity?
Maximum.
Maximum, absolutely right, because there we're at equilibrium. And then what about position? Oh, I just said it. What's our position?
Equilibrium.
We're at the equilibrium. We could say that it's the 0 displacement, any of those, because we are at the equilibrium. That's when our velocity is maximum. That's where our acceleration is 0, that sort of thing. Is there anything else left on this one? If you wanted to make a spring oscillate with greater amplitude by applying a force, when should you apply the force? If you want that spring to stretch even further, and you had to choose when you're going to apply a force, when are you going to apply that force? It's kind of a tricky question. What do you think?
Once at the equilibrium.
See, I would do it when it's already fully extended to its maximum displacement. If I applied a force then, it would cause it to have even greater displacement. So here, I would say at max displacement, because that force would cause the displacement to get even bigger. What will that cause? An increase in the amplitude, increase in displacement. Now, in my opinion, I think this backside is something that takes getting your mind to wrap around, and it's okay, totally okay. Understanding the very first graph, I'm going to scroll it to where we go back to that first graph. Understanding that first graph, that's the important one. That's absolutely the important one. Everything else is derived from it, but understanding that first one is the key to all of this stuff. I'm going to give you a second on that. I want to get us started on what's essentially the homework page. It's 2 pages, but we can kind of clip through most of it together. Let's say 10:15 kind of being the cutoff. That way you have time to stretch, get a drink of water, get out of your seat before you have to sit down through second period, which definitely won't be as much fun as first period, but it never really is, right? So I tell myself, except for my second period students, I tell them second period's the best. But let's see, let's go into those practice problems. Let's take a look at this. We'll go through these together over the next few minutes until I get tired, you get tired, and then so when max, I'm sorry, that might be an old question. So when velocity is max, acceleration is zero. Absolutely, because velocity is increasing and acceleration is decreasing. And when after acceleration hits zero, acceleration is going to change directions, and then it'll start slowing down the velocity. When acceleration changes directions, it then opposes the velocity and slows it down. So acceleration is increasing in magnitude all the way through until acceleration hits zero. When acceleration hits zero, now velocity has hit its maximum velocity, and then it's about to start slowing down. So when you said velocity is max at acceleration zero, yes. And because the reason is after that, acceleration is going to change directions and slow things down. That's the why. Let's just take a look at this and answer these. Some of them will spend more time than others, just depending on the question. For each motion below, indicate whether the motion is periodic, simple harmonic, or both. All right, a child swinging on a playground swing. Is it periodic? Yes or no? Yes. Awesome. All right, when I say yes, like that means it showed up in the chat. Yes, that is periodic. We could time that. And it repeats itself. Is it simple harmonic? Yes, you don't have to put the question mark. Absolutely, it's simple harmonic. There is a restoring force. You know how you can tell if there's a restoring force? Does the object slow down and change direction? And absolutely, a child on a swing is just like a pendulum. Goes up, slows down, comes back the other way, slows down, comes back the other way. So absolutely. What about a CD rotating in a CD player? Once, I know we don't listen to CDs anymore, but they do exist. A CD rotating in a CD player once every 0.29 seconds. Is that periodic?
Yes.
Absolutely. Is it simple harmonic? Correct. It is not simple harmonic. No, because it doesn't change directions. It does not have a restoring force. It's just going one way. It's like the earth going around the sun, just one way. So be careful on that. All simple harmonic are periodic, but not all periodic are simple harmonic. It's like all squares are rectangles, but not all rectangles are squares. Something like that. All right, an oscillating pendulum and a grandfather clock. Oscillating pendulum, grandfather clock, is it periodic?
Yes.
Yes, absolutely. We've already talked about that. And then is it, it's got to be simple harmonic. I'm not even going to ask that one because we've used that as an example for simple harmonic. The moon in a circular orbit around the earth, is it periodic?
Yes.
Yes. Is it simple harmonic?
No.
No, heck no. No restoring force. It goes one way. We time it. It's the moon doesn't go halfway across our sky and then stop and then change direction to go back down. That would be kind of cool, but it doesn't really happen. All right, so let's take a look. That was the easy one, just to kind of get us to relax and say, wow, the graphs kind of sucked, but now everything seems a lot better. Okay, so now we have as a pendulum bob moves closer to its equilibrium position. So here's my pendulum bob, and it's going to the right. As it moves towards its equilibrium position, how does the magnitude of the restoring force change? Okay, so how would we describe what's going on with the restoring force as the pendulum bob goes towards that equilibrium?
It would be decreasing.
Say again?
Decreasing?
It decreases, absolutely. How does the magnitude of the restoring force change? It is decreasing. And the way that we would explain it is the restoring force, is equal to let's see, displacement. How do we describe that? The restoring force, how about this? I want to use words. I don't want to use an equation. I want to say that the restoring force is proportional to the displacement. As the displacement increases, the restoring force increases. So as the displacement decreases, the restoring force would also decrease. Yes, so I've got is at max when it's farthest away and decreases as it gets closer to equilibrium. Yes. So make sure that as we're explaining things, I even started to write an equation. Let's avoid equations if we can, and let's use words to explain. All right, what about how does the magnitude of the tangential acceleration along the direction of motion change? How does the magnitude of the tangential acceleration? The tangential acceleration is the acceleration this way. Okay, now the reason it's specifying it because we know that a pendulum is moving in a circular path. So there is a centripetal acceleration going towards the center, but it's saying the tangential acceleration. How does the magnitude of the tangential acceleration change as we approach the equilibrium position?
It decreases.
It absolutely decreases. So again, I'm going to put decrease. Because we know that when we get to equilibrium, tangential acceleration goes to 0. Now there's still a centripetal acceleration because we are in a circular path, but that centripetal acceleration is different than the tangential acceleration. All right, we've talked about circular motion. Don't leave that knowledge behind, but just know it's the tangential acceleration that we're talking about going to 0 as we get to acceleration. What I wrote down was tangential acceleration goes to 0 when the pendulum bob reaches the equilibrium position. It's just a kind of a factual statement is how I explained it. How does the magnitude of velocity change?
It increases.
Absolutely increases. So here I wrote velocity is at its maximum as the pendulum bob moves through the equilibrium point. Velocity is at its maximum as the pendulum bob moves through the equilibrium point. These are all things that we've talked about. It's just kind of putting terminology and definitions into questions and answers. How does the magnitude of the centripetal acceleration change? Here's your tricky one. How does the magnitude of the centripetal acceleration change? What do y'all have?
It doesn't.
What if we did this? Off to the side, I want to define again what centripetal acceleration is. Now it's fair. We've all had a break and we've actually studied something since we did centripetal circular motion. But what if I told you that centripetal acceleration is equal to velocity squared divided by radius? If I told you that, or if I reminded you of that, now what would you say about centripetal acceleration as you approach equilibrium? Say it one more time.
It increases
Why?
because the velocity increases towards the equilibrium.
Exactly right. The tangential velocity is increasing. And we can see that centripetal acceleration is tangential velocity squared divided by radius. So if the velocity is getting bigger, centripetal acceleration is getting bigger. Okay, so don't forget, when we get to May and we get to that test, we're going to be grabbing bits of information from each of these units and putting it together. And that's what we're seeing here. So what's that?
Mr. Watley,
Yeah,
I
what's
have
up?
2 questions.
Okay.
So since the centripetal acceleration is increasing, wouldn't the centripetal force increase as well?
Wouldn't what increase as well? I'm sorry.
The centripetal force.
Yes. Yes. The centripetal force is increasing, but the restoring force is 0. The restoring force is tangential, bringing you to the equilibrium, but the centripetal force is that force that causes you to change direction and stay in a circular path.
All right. And my second question was, when you're at your maximum displacement or amplitude, isn't your acceleration at its maximum as well?
Your tangential acceleration is maximum at amplitude, where your centripetal acceleration would be minimum because your velocity is zero.
Okay. Got it. Thank you.
Absolutely. And those are very, very good questions. And if you're listening in this class, I would write down the questions he said and write down the answers, because Pius is bringing up very good points and things to help keep it organized in your mind. So these are very valid things he's asking, and things that if you're listening and saying, okay, that makes sense, write it down. Or if you're like, what is he talking about? Write it down. If you're like, this is so easy, then cool. I'm glad. I want it to be easy, but it doesn't always start out that way. We got just a bit more time. I tell you what, let's look at number 3 and see how far we get. I'm going to scroll this up. When an acrobat swinging on a trapeze, okay, so I'm sorry, I'm totally a visual person, so I'm going to draw my little acrobat. There they are. And there's my little line saying they're in motion. Swinging on a trapeze reaches equilibrium position. Oh, cool, I drew them equilibrium. The net force acting along the direction of motion is 0. Okay, so when it's saying acting along the direction of motion, that's the tangential. Okay, that's the restoring force. Why then does the acrobat swing past the equilibrium position? So if the restoring force is 0 right there, why do they keep moving?
Because
Because
they
their
still have,
velocity is not 0.
Correct. Now, someone else was talking along with you. What was she saying?
saying that they still have velocity.
Correct. Now, force is not, force has to do more with acceleration than velocity. Just because your force goes to 0, that means your acceleration goes to 0. That doesn't mean you stop. If I throw a baseball out into outer space, let's say I become an astronaut, or they take a teacher into space, and I go up there with a baseball and I throw it out into space, and then I come back home, there's no force currently acting on that ball, but it's still moving, right? So just because the force goes to 0 doesn't mean you stop. That just means whatever motion you have, you're staying in motion. Newton's first law, object in motion, right? So I answered this when I wrote down my answer. I said velocity is increasing as the acrobat approaches the equilibrium position. Though net force is 0, velocity is at its highest when passing through equilibrium. That's the way I explained it. Is it the best way? Certainly you can come up with something better, but it's not wrong. All right, it's 10:15, but I kind of want to set up at least one problem together. So let's look at the start of number 4. Then I'm going to turn it over to you guys and let you have the next 2 days to work on things. So let's scroll this up, and it says calculate the period and frequency of a 3-point. So we want period, we want frequency, and they've told us that the length is equal to 3.5 meters with the following locations. North Pole, with where they tell us gravity. Okay, now we're looking for period and frequency. Well, I know that period of a pendulum is equal to 2 times pi times the square root of L over G, right? My G looks terrible, but hey, it's what I got. If I was to plug this into the equation, then I would say that the period of my pendulum is equal to 2 times 3.14 times the square root of 3.5 divided by, they gave me a number, so I have to use that number, 9.832. Okay, so we need to put that in our calculator. I would do 3.5 divided by 9.832. I've got that division, so now I'm going to take the square root of that and then multiply that by 3.14 and then multiply that by 2. And what did I get? I got 3.7469, blah, blah, blah. All right, so I did get the period of my pendulum is equal to 3.7. I'm going to round it because I don't do more than 2 decimal places, 3.75. And then if I want to get the frequency, I'm just going to invert that. So 3.75 inverted. It gets me 0.266666. So 0.27 hertz. This is seconds. Not too bad. Let's see, what time is it? Oh, it's getting really close. I'll tell you what, that gave us, we went through all the conceptual questions and we've done the first of the problems. You've got the number 4, the rest number 4, then there's a number 5, 6, 7, 8, and 9. So not terrible. Let's have this due by start of next class.